So whether you see it in the mRNA or you see it up here, the point is there's a redundancy of the genetic code. They call that the degeneracy, which sounds like a breakdown, sounds like a bad thing, but it's actually a good thing. There are, calculate this box, right? 1, 2, 3, 4, and calculate up that way. There's 64 different codons. Or if you want to think of it in terms of anticodons, there's 64 different anticodons. Okay. How many amino acids are there? 20. Maybe if you're a baby, 22 at the most, right? How come there's so many more codons than there are amino acids if every 3 letters is one codon? There are more combinations of those 4 letters than there are amino acids. Does anybody remember doing permutations in statistics? There's 64 different combinations of those 4 letters. A, C, U, and G. 64 different combinations, 64 different codons. But there are only 20 amino acids. So that means there must be more than one codon per amino acid. Okay, so let's take out the ones that say stop and the one that says start.
It doesn't say start on that, but
yeah.
it's
No.
Where is it?
AUG in the finding.
AUG?
Bottom left, go up one.
What here is AUG. The first is A and then U.
I'm still not seeing AUG.
All the way to the left.
Here?
Yeah.
Yep, that's your start cut off there.
I don't know how to mark on that document. There is a table in your textbook which is better to use. It's just that the textbook didn't give me a figure of that one. And the theanine is always the start. I can see if it's in your PowerPoint, but I don't want to take time.
It's in the book.
Yeah, but it's not in the PowerPoint? I have to look in the PowerPoint. Okay, so subtract start and stop. So you subtract 4. So that's 60 different codons for 20 amino acids. So a lot of the amino acids have more than one codon. And let's say the cell is reading, and it reads CUC. And it'll give you leucine. But if it reads CUU, it'll still give you leucine. The reason they think this is because in terms of evolution, cells over the millennia made mistakes sometimes. Now you're typing, and there's always that one word you misspell. For me, it's remember. Every time I type remember, I leave that second M out. I don't know why. So I go in my spell checker, and I tell my spell checker every time I type remember, make it remember. You know, and it fixes it automatically. So this is like a fail-safe mechanism. So the redundancy or the degeneracy of the genetic code is considered a fail-safe mechanism. So even if the cell makes a mistake in that 3rd letter, you still get the same amino acid. So let's say my mRNA had a mistake in it because there was a mistake in the DNA, because it's a mutation. But I still get the same amino acid. That means the mutation exists, but it's not expressed as a change in the protein. If I get the same amino acid, my protein is not changed. And that's how it's a fail-safe mechanism, because they think that cells over the millennia made mistakes sometimes in that 3rd letter, and so cells evolved to compensate for that. All right, you got the wrong letter, but the cell's going to still call on the right tRNA molecules. It's going to be fixed. It's going to get the same amino acid anyway. So it's like if you type THA, and the cell automatically says, I know she means the, so we'll just go with the. So it's a fail-safe mechanism. You get the same amino acid, even though there might be a mistake in that 3rd position. So apparently, if you're an evolutionary biologist, you're thinking, that 3rd position is where a lot of the mistakes happen. Must be something significant about that 3rd position, that's where mistakes happen. and they call that the wobble position. I love that. Of all the scientific terminology you have to learn all semester, all of a sudden they decide to call it the wobble position. I'm like, really? Because it can wobble between different letters and you still get the same amino acid. So the result is called the wobble effect. And then I thought, well, I kind of like wobble because wobble rhymes with gobble, and I'm already working with turkey feet, so it's all going to work out okay. Wobble, gobble, turkey feet. So they call that the wobble effect. This is what you call a silent mutation. So it's a fail-safe mechanism. The redundancy is a fail-safe mechanism that results in silent mutations. In your handout package, there's an explanation of genetics and mutations and different kinds of mutations. So, this is a silent mutation. If you have the wrong letter in the third position, but you get the same amino acid anyway, the protein is not changed, so the mutation is silent. The mutation does exist. You have a typo. You have the wrong letter. But it doesn't manifest as a change because you're going to get the same amino acid anyway, so your protein's going to be normal. That's a silent mutation. What were the other kind of mutations we talked about? Oh, we talked about missense mutations. A missense mutation means it makes sense, but it's the wrong amino acid. So a missense, a letter is changed, you get a different amino acid. That letter is more likely to be in your first or second position. And a nonsense mutation is when you get a wrong letter that results in no amino acid. Maybe you get something like a stop or a start where you should have an amino acid. That is a nonsense mutation. So think of no sense. Doesn't make any sense. There's no amino acid. So missense, nonsense, and silent mutations. You need to know those, and it's in your handouts package or in your textbook chapter 7. We're also going to talk about point mutations and frame shift mutations. Okie? I think I can put my screen up. Just for now. Okay. I'm going to go long ways with my DNA. And we're going to simplify my codons just to make it easier for you, okay? So we'll do CCC is the first codon, GGG is the next codon, AAA, and TTT. So this would be GGG, CCC, TTT, AAA. My sense strand, or my template strand, my antisense strand or my complementary strand, coding. Coding strand, template, coding.
Okay.
That's why I always went with sense and antisense.
So wait, that one is sense.
The coding strand means it carries the code to the next generation. Template strand is the one you're going to make your proteins off of. All right, forget all of that. Just remember DNA is double-stranded, I had untwisted and all that. Okay. Let's say I have a mutation when this is getting copied. I have a mutation right here. Instead of getting a G, I get maybe an A. That's the mutation right there, right? That's called a point mutation. when the DNA is being copied, a mutation occurs at one point, at one letter. And what are the letters called? Bases, right? What are the bases? A, C, T, G, whatever. It occurs in one base. Therefore, it's also called a base substitution mutation. Because it happens at one base or one point. Now, if it's in my third letter, when I make my mRNA, I'm probably going to get CCU, and I'll still end up with the same amino acid anyway because it was in the wobble position, right? So it might result in a silent mutation. What if the mutation happened up here? Now I might get a different amino acid. Then I have a missense mutation. If a mutation occurs in a spot that results in a start or a stop codon, then I have a nonsense mutation. Any mutation that occurs at one letter is called a point mutation or a base substitution. So this can include all different types of mutations like silent mutation if it's in the third letter, in wobble position, right? Okay, sorry, all of a sudden my stomach just came on. I'm like clockwork, man.